Okay, this video talks about exact differential equations. Apparently, I'm redoing the video again because I didn't do things easily. Clearly. So apparently, let's do this more clearly. So imagine we have a question. It's in exercise 6 1a. So apparently, we have this question y squared plus. So we have this question over here. Okay. So apparently, what does this? What is actually exact differential equation? Okay. So apparently, exact differential equation are that let's say you have a okay, let's straight away get the final result. Okay, let's get the final result over here. Let's let's say if we have a equation, we call it xi. Okay, is equals to y squared x plus x squared y plus x plus c. Okay, we have this equation over here. If someone call you to differentiate, okay, how do you differentiate? So typically, if you were to differentiate, it's partial xi, partial x. You clear away all the x's first, and then you plus. I mean, partial xi and partial y. You'll get f prime xi, right? So this is how it works. So this is also why we have this. So this portion is actually this. Okay, so it's just xi dx plus xi dy equals to in this case is 0. Okay, so this is one approach in doing in knowing, okay, in knowing the relationship or the intuition behind exact differential equation. So alternatively, you can also do in terms of another method, which is typically if you were to run an experiment, okay, uh, you have two equations. Let's say you have equation A, you have equation B, okay, and you see that B, if you add A and B together, you have 0, which is a very good phenomenon, right? You see that, okay, A is equals to B. That's the thing. So how do you do it? Okay. So exact differential equation can be how do I say it? Represented in terms of this form or this form. So if you want to make it exact, if you want to make it in terms of this, one way is to multiply the whole equation in terms of dy. For this case, in terms of dx. So therefore, if you were to see properly, if you multiply dy into it, you cancel away dy over here and you times dy over here, which is the same as this, right? So dx also, you get this. And then another thing is that it may not be exactly 0. It may be, let's say, if we have another example, let's say we should have y squared um, plus 2xy plus 1 dy dx, and then plus 2xy is equals to minus x squared. Okay, so this is your result. So you want to solve, because you have the result already. You want, typically normally you want to make it you want to create an equation that contains all this stuff. Okay, because these are all information of your experiment, so you want to have an equation that can contain all your data into one equation. You want to mix them all together. So what you want to do is to bring this over. So this will be plus equals to 0, right? And then this will be this form, isn't it? And then you just do the same thing and then you get. So this is what I want to convey over here. So without further ado, let's start. So to tackle this problem, as I said earlier, the original equation xi. Okay, let's take the original equation xi. This is the final answer lah. Okay, so if you were to partial them, if you want to solve for f prime xi, is partial xi partial x partial xi partial y, right? So can I say that if partial xi partial x multiplied by partial y, is it equals to partial x. Okay, so if you were to differentiate in terms of y, okay, and if you were to differentiate in terms of x over here, are they the same? They are the same. Okay, so this is why if this is the same as this is exact. So this is what we are doing in this portion. So let this be m. Okay, we call it m. Okay, and then if this portion is actually this one, so you can you want to differentiate partial in terms of y lah. Okay, so whatever thing that is, let's say you have dx, you just differentiate in terms of the opposite variable, which is dy. If it's dy, then you differentiate in terms of the opposite variable dx, which is what here over here. If it's x over here, then you differentiate in terms of y. If it's y over here, you differentiate in terms of x. So this is what it plays, and then let me clear away all this, and then put away all this, and then if you were to differentiate in terms of y for m, you get this. If you were to differentiate in terms of n, you get this, and therefore they are exact. Okay, because 2y plus 2x is the same as 2y plus 2x, right? So the first step is for you to do is actually to for you to do is actually to test for the exactness. Okay, so to test for exactness, this is what you're going to do, and then since both of exact, we can solve using the exact method. So the exact method wise is, let's go back to the original problem, which is this one. Okay, it's the same as this. I just write it in terms of n and n. So for m, since we can see that m is differentiated in terms of dx, okay, as you can see, as I say earlier, the xi, if you want to differentiate them, you have to you differentiate in terms of xi partial x, or it can be written as xi dx plus xi dy, or m dx plus n dy. Okay, it's the same thing. Okay, so apparently you see this relationship already, and therefore we want to attain this equation. Okay, our objective is to attain this equation. Okay, that contains all of this information. So what we're gonna do is to integrate m, since we know that if you were to partial xi in terms of, because if you differentiate xi, okay, you're partialing xi in terms of x and partialing xi in terms of y. So if you were to integrate in terms of x, you are getting back some xi, some information on xi, because let's say if you were to integrate, let's say this is the original equation, you differentiate in terms of x, you will you destroy all the y information, right? And then if you were to differentiate in terms of y, for example, let's say if you were to differentiate in terms of y, you definitely x is gone already, right? So you are already missing some information. So therefore we want to piece out the information. So this is what we're gonna do first. So to do this, we want to find the original equation first. We want to have a glimpse of the original equation. So apparently you integrate in terms of n. So for m case you integrate in terms of dx. So we do this form. Okay, we do this form. And then hold on, I try to clear away all the rubbish. So apparently you get this equation. Okay, because you know that it may contain some information of fy, as I said earlier. Okay, some information that may be lost. So we put in function of y in case. And let's name this equation xi, which is our original equation. Okay. So alternatively, you don't need, in the test you don't need to do two times. Okay, you just do, I just want to prove that if you do this and if you do this, the two methods will derive the same answer. So let's say if you were to do in terms of n, you integrate in terms of dy, you'll get this information. You'll get this equation. Let's write fx, some function of x. Okay. So therefore, the next thing is to find your function of x, because this is your xi. Okay, this is your xi, your original equation. You already see your original equation, but just that you don't know whether, because you're lacking some information. You don't know what is function of y in this case for the m. Okay, for m you don't know what the hell is this, and for n you don't know what the hell is this in the function of x. So therefore, one thing you need to do is to one method you do is to differentiate in terms of the function that is missing lah. Okay, so let's say if you are doing with m, we differentiate in terms of y. Okay, so if you were to partial differentiate in terms of y, you get this equation. Okay, remember, always kind of mistake is that you forget to put f prime y. Okay, or you didn't realize, so you just put it f prime y. So you're just simply differentiating this thing. Okay, and therefore you compare with n, which is the partial, as I say earlier, um okay, as I say earlier, okay, sorry, as I say earlier, the very early times, as I say, well, what am I writing? Sorry, partial equals to something equals to f prime xi. So this is also can be written as xi dx plus xi dy. Okay, can be also written as m dx plus m dy, right? So therefore you know that if you were to differentiate the xi, partial differentiate xi in terms of y, you get n, you get this, you get this, right? You get this portion over here. So this is what we want to do, because we want to compare and find any missing function in there. So therefore we differentiate in terms of y, and we realize that, okay, when we compare, we realize that f prime y is equals to 0, because as you can see, this when we differentiate this partial xi, our glimpse of the original equation, we realize that they are the same, just that f prime 1 is nothing. There's no f prime 1 in there, so it equals to 0. Alternatively, this method for n, you can see actually there is some function of x. So what we mean is that, let's say now we deal in terms of n. Okay, take note that this equation is different from this equation because your approach is different. Okay, so therefore you have this as the xi in terms of the n thing. So therefore if you were to partial differentiate in terms of x, okay, if you were to partial differentiate in terms of x, you get this equation. And if you were to compare with the original problem, this one, you realize that the f prime x is actually 1. Okay, this is the same, this portion is the same as this portion, right? And you realize that f prime x is equals to 1. Okay, let away the c, the c is some any constants. Okay, so therefore you know that the you know that we're lacking something. The information is lost in here. So this is the lost information we already found. Now we find we have successfully found the lost information, because as I say, if you were to partial differentiate this equation in terms of y, you are clearing away the x, right? The x is gone, so you lost the information over here. So this is why when we approach in this manner, you will eventually find back this x. You see, so it's like a lost and found game. So therefore Therefore, since we know that f prime x is equals to 1, we want to find back the original equation. This is our king equation already, right? That's that we want to solve for the function of x. So we just integrate the f prime x. So we just get x. And when you sub in this x into our function of x, you get our final equation. And both approach, as you can see, are have the same result. Okay. It takes time to sink into it and you need to go and practice. I would suggest you go and practice a lot of questions in order to fully understand the whole iteration. And next video I'll do, actually I've already done the next video because um let's show you. I actually did a video on the same thing that I'm talking now, just that it's not adequate enough. So yeah, next video there's an example so you can just do it. Okay, so see ya.